Okay, so shall I start now, or so
Just
I
wait.
is still left here. 1 minute is left. So shall I start?
Just we can wait for 1 more minute.
Yeah, sure, sure.
Okay, so good morning and welcome to all. Uh, Today we have Eshita Mazumdar, Dr. Eshita Mazumdar from ISI Bangalore, and she will be speaking on iterated sumsets and Hilbert functions. So the slides of this talk also available on our web page. So if you want to access, you can access from them. So yes, Eshita, you can start.
Well, thanks a lot. I am Eshita Mazumdar, uh, a visiting scientist at ISI Bangalore. Today I'm going to talk about my most recent research work, which is on iterated sumsets and Hilbert function. It's a joint work with Professor Salam Eliahu, and here we are mainly interested in uh, build in we are mainly interested to recover Plunki's inequality. And the beautiful thing is that while doing so, we are able to establish a bridge between a century-old Macaulay's theorem in commutative algebra and iterated sumsets in additive combinatorics. And the whole process leads us to an extremal problem to us as well. Well, before starting uh, the talk, so let me take some usual convention that whenever I will say a group G, it means it is an abelian group. The structure imposed on it is an additive structure, and 0 being an identity element of the group. So, for example, one can think Z as such abelian group. Okay, I mean Z is an example of that. Let AB be any two subset of the abelian group G. In that case, we define some set of AB as the set of all points of the form A plus B, where A belongs to A and B belongs to B, and we denote that set as A plus B. If it happens that A is equal to B, we call this subset as, we denote this subset as 2A. And in general, when H is greater than equal to 2, we defined HA as A plus H minus 1 of A. And we call this HA as H-fold subset of A. In particular, when H is equal to 0, we said that 0-fold subset of A is a set containing the identity element only. And when H is equal to 1, the one-fold subset of A is the set A itself. A typical problem in additive combinatorics will be to study the growth of cardinality of H-fold subset of A while H is also increasing, and my set A is a finite set. In this particular talk, we are mainly interested to study about the cardinality of H plus minus 1 fold subset of A when the cardinality of H fold subset of A is given. Well, in this connection, in 1970, using uh, the graph theoretic result, Clunake stated that if I have a integer age greater than equal to 2, and if A be a non-empty finite subset of an abelian group G, then we can say that cardinality of I-fold subset of A is greater than equal to cardinality of H-fold subset of A power I by H. Here I is running over 1 to H. Now this classical result is equivalent of saying the case that I equal to H minus 1, that is cardinality of H minus 1 fold subset of A is greater than equal to cardinality of H fold subset of A power H minus 1 by H. Now, as I said earlier, our main aim is to recover and strengthen Clunake's estimate. Now, how to do that? We are mainly following the 2 steps. First of all, corresponding to a finite set A, we are going to construct a standard graded algebra RA, such that this standard graded algebra has a Hilbert function which are same as the cardinality of H-fold subset of A. Once this step will be over, we will following our next step where we apply the Macaulay's theorem on the growth of Hilbert function. Now, before seeing that how we are constructing this standard graded algebra, I would like to introduce some definitions. So first definition is the standard graded algebra. Suppose I have a commutative algebra R over a field K, so that R can be written as the direct sum of Ri's, and each Ri is a vector space over the field K. We can say that this R is a standard graded algebra if 3 conditions hold. First of all, this R0 is my field K. Ri Rj is a subset of Ri plus j for all ij greater than equal to 0, and R is generated as a K algebra by finitely many elements in R1. Now, once we have this structure for R, we can say that each Ri is finite dimensional vector space over K, right? Okay. Now, coming into the next definition. So let me consider the standard graded algebra R. So clearly, we can say that Ri is a finite dimensional vector space over the field K. So we can define a map from this set to this set, which will take I to dimension of Ri. Now this particular function is known as Hilbert function corresponding to the standard graded algebra R. Now move to the next definition. It says that suppose we have 2 positive integer a greater than equal to I. Then we can say that there exist I unique integers in increasing order. All are non-negative, so that A can be written as sum of the binomial coefficient of aj, where j is running from 1 to I. This kind of representation of A is known as ith binomial representation of A. Once we have the ith binomial representation of A, we can define A power bracket I as summation of the binomial coefficient of aj plus 1, j plus 1, where j is running from 1 to I, and 0 power bracket I as equal to 0. For example, we will have that 100 power bracket 5 is equal to 152. Now the question is that how we are arriving at this stage. For that, I'm taking A to be is equal to 100. And I'm taking I to be equal to 5. Now clearly I will have 5 this unique numbers, so that the fifth binomial representation of 100 is nothing but this thing. Once I have that, using this formula, we can say that 100 power bracket 5 is equal to this quantity, and if we evaluate that, we will have this value to be 152. Okay, now we will see that how by knowing this definition, how can I construct a standard graded algebra. So first of all, at this moment, what we have is that A is a non-empty finite subset of a abelian group G, and K is my commutative field. What I wanted to do is that I wanted to associate a standard graded algebra RA. So Hilbert function exactly models the sequence cardinality of H-fold sumset of A, right? Now how to do that? We know that we have a group, abelian group G. So what we can talk about is that the group algebra. Let's say KG be my group algebra. Now, once I have the group algebra, I can say that its canonical K basis is the set of symbols T power G such that G belongs to the group. And the product is induced by the formula T power G1 into T power G2 is equal to T power G1 plus G2 for all G1, G2 belongs to G. Once I consider this group algebra, now in the next step, I'm considering the one variable polynomial algebra over this group algebra, and I'm calling it as S. Now this S has a natural K basis, which is the set of collection T power G, X power N, where G belongs to G and N belongs to the set of natural number. If I take any two basis element let's say T power G1, X to the power N1 and T power G2, X power N2, then this multiplication is given by T power G1 plus G2 and X power N1 plus N2. And if I take any basis element from here, its degree will be defined as equal to N. Okay. In that case, we can say that S is equal to direct sum of SH, where each SH is the K vector space with basis the set containing T power G, X to the power H, such that G belongs to the group G. In this situation, my set S is a graded K algebra. Now we have that as the finite set A. So let A is equal to, A is a set containing the elements A1, A2 up to AN. Now we define Ra to be the K subalgebra of S spanned by the set this, which is the set containing T power A1 x, in this way T power AN x. Clearly, Ra is finitely generated over K by elements of degree 1. And this confirms that Ra is a standard graded algebra. Clearly, R can be written as the direct sum of RH, where this RH is a K vector space with the basis set T power B x to the power h, where B belongs to HA. This will ensure that dimension of RH is equal to cardinality of H-fold sumset of A. So our first step is over. That corresponding to a set A, a finite set A, we are able to construct a standard graded algebra. Now let us see that what is our Macaulay's theorem. In 1927, Macaulay stated that the numerical function I goes to di is a Hilbert function of a standard graded algebra if and only if, first of all, d0 is equal to 1 and di plus 1 is upper bounded by di power bracket I for all I greater than equal to 1.
Ishita,
Yeah,
sorry to interrupt. There is a question in the chat box.
yeah.
How do we calculate these edges in the binomial representation?
Sorry, how do we?
Calculate these edges in the binomial representation. That's what the question says.
Age, just a second.
Like you can see in the question
Can you
chat.
tell me the which slide are you? Which
Uh,
slide number?
Gargi, can you speak up and
Huh?
this is a question from Gargi leather. It's like in the chat box. Can you check?
Okay, just a second. I'm not able to.
It's on that slide where you talk about binomial representation.
Hmm?
So my question is, it's on that slide where you talked about binomial representation.
Can you tell me the slide number?
Yeah.
It is right hand side below. You will find the slide number.
Yeah, just a second. It's on slide number 6.
Okay. Yeah. So you are asking me this thing that what is the guarantee that these AIs are exist, right?
Actually, I'm asking that how do we calculate these AI? Suppose instead of 100, we take 1,000 here. So,
Yeah.
like as.
Okay. So for example, let's say we can start with some smaller number. We may start with it. Okay. So try to so say you have, okay, for this thing, let's say I'm talking about this 100 particularly, okay, because we have this example here. Or because if you, okay, let's consider 1000. I don't mind if you wanted to take that one as well. Then first try to calculate the binomial, just a second, and you wanted to find out the fifth binomial representation, let's say. Okay, so you just try to find out the largest possible values, this AI, okay, so that it will cover your A. So let's say corresponding to 5, I mean, if you are fixing your I to be equal to 5 and you're taking your A to be equal to 1000, so go to 1000, I mean, binomial coefficient to be as like some number, I mean, binomial coefficient is, let's say, x 5 you are considering, okay? So you are trying to find out this x to be the largest one so that it will cover maximum values of A. Okay, now the remaining part will be a positive number again. Then you will again take your j to be equal to 4, and again you will try to find out your another y, so that this A minus x 5, I mean, A minus binomial coefficient of x5 will be covered up. You will see that you will cover some part, but you are not able to cover the whole. So you take that part again. So this process will go on. Is that okay? I mean, what I'm trying to say is that that part is okay?
I'm still not able to get that
Okay.
covering
Okay.
wala.
It's like that. For example, so let's say let's take any small number. Let's take you are taking 10. Okay, and you are trying to find out binomial coefficient of, I mean, this binomial representation of 3, right? So what is the value, what is the largest possible value of x, so that this 10 minus binomial coefficient x 3 is greater than equal to 0? That you need to find out. Okay.
Okay.
What is the largest value of x? Once you have that number, you will be, are you getting my point?
Yes.
So then you will have this remaining number, right? This 10 minus x by x, sorry, 10 minus binomial coefficient x3. Then this for this remaining number, let's call it as b. You will again do the process for binomial coefficient 2. So you will go for the largest value y, so that b minus binomial coefficient y2 is greater than equal to 0.
Okay.
You will do that process again and again.
Okay. Yeah, thank you.
Is that okay? I mean,
Yes, ma'am. Yes, ma'am, it's fine.
It's fine, right? Okay, so shall I move further?
Yes, ma'am.
No. Okay, so where I was, okay, so I have completed this much. So now I have already, yeah. So I have introduced this Macaulay's theorem already. Now, the next thing is that once we have this Macaulay's theorem and our the construction which we already derived, we will have that, we can say, the following result. So it says that, let's say h greater than equal to 1 be any integer, and I'm taking A to be a non-empty finite subset of a finite abelian group G. Then since I'm taking the finite abelian group G, so again I can construct that previous standard grade algebra, and so that Hilbert function is same as my cardinality of H whole subset of A. And if I use the necessary part of this Macaulay's theorem, that will give us from here that cardinality of H plus 1 fold subset of A is upper bounded by cardinality of H fold subset of A power bracket H, right? Okay. Now, there is another version of Macaulay's theorem which has been proved by Eliyahu in 2018. Before introducing that theorem, so let me introduce the notion which says that if h is a natural number and x is a real number, then the binomial coefficient xh is denoting this particular number. Okay. Now, this condensed version of Macaulay's theorem tells us that if we have a standard graded algebra R over the field K with Hilbert function di, and let's say a is greater than equal to 1 be an integer, such that we have a unique real number x greater than equal to h minus 1, so that dh is equal to binomial coefficient of xh, then we can say that, first of all, lower bound of dh minus 1 is binomial coefficient of x minus 1, h minus 1, and upper bound of dh plus 1 is upper bounded by binomial coefficient of x plus 1, h plus 1. Now, again, using this result and the construction which we did earlier, we can say that if h greater than equal to 2 be an integer, and if A is a non-empty finite subset of the abelian group G, if it happens that x greater than equal to h be a unique real number having the property that cardinality of h fold subset of A is binomial coefficient of xh, then we can say that cardinality of binomial coefficient of h minus 1 fold subset of A is lower bounded by this quantity, and cardinality of h plus 1 fold subset of A is upper bounded by this one. Well, it has been observed that it is much more easier to handle this theorem rather than the previous theorem. Okay, but we have observed that for x greater than equal to h, if cardinality of h fold subset of x is equal to binomial coefficient of xh, then our previous result gives us much better bound than this bound. Well, now let me trying to compare all those results. So let's say G be any abelian group, and I'm taking A to be a subset of G such that cardinality of 5A is equal to 100. Now, Plunke's inequality yields that cardinality of 4A is lower bounded by 40, and cardinality of 6A is upper bounded by 251. Now, the condensed version of Macaulay's theorem gives much better bound than this Plunke's inequality. It says that cardinality of 4A is lower bounded by 58, and cardinality of 6A is upper bounded by 161. But the first result which we have is give us the much sharper bound. It tells us that cardinality of 4A is lower bounded by 61, and cardinality of 6A is upper bounded by 152. Well, now, the natural question is that how far we are from the optimal bound. And this natural question forces us to define an extremal problem, which is for that we are defining the extremal function omega g HIM for a group G and for positive integer HIM. It is defined as the minimum of the cardinality of I-fold subset of A if I is less than equal to H, and maximum of cardinality of IA if I is greater than equal to H, where the extremum is taken over all some subset of A of G satisfying cardinality of HA, cardinality of H fold subset of A to be equal to M. As we observe that omega G of 5400 is greater than equal to 61. This we have already, and omega G of 5600 is upper bounded by 152. But we have much better bound if we took G to be is equal to Z and G to be equal to Z. We observe that if my group is Z, then for this set, even for this set, we will have that cardinality of 5A is 100, cardinality of 4A is 63, and cardinality of 6A is 144. Well, we believe that for the group G equal to Z, these are the optimal bound. In particular, we conjecture that omega Z 5400 is 63, omega Z 5600 is equal to 145. Well, now, since we are talking about the Pluna-Case inequality and we are trying to recover it, and we have seen that we have already recovered Pluna-Case inequality. Now we're trying to write our theorem in terms of Pluna-Case. Before that, I wanted to introduce a notion which is saying that if H is a positive integers and let's say X greater than equal to H be a real number, then I'm setting theta xh as H by X into binomial coefficient of xh power 1 by H. Now the condensed version of Macaulay's theorem tells us that if H greater than equal to 2 be an integer and A is a non-empty finite subset of an abelian group G, then cardinality of H minus 1 fold subset of A is greater than equal to theta times cardinality of H fold subset of A power H minus 1 by H, where the real number X greater than equal to H is greater than equal to H, and cardinality of H fold subset of A is equal to binomial coefficient of Xh. So here we are giving the Pluna-Case form. Moreover, we can say that this theta is greater than equal to 1. So when theta is equal to 1, we will have the Pluna-Case inequality. But the moment when theta crosses the value 1, it will give us much strong, it will recover my Pluna-Case theorem. Now let's see that how the proof goes. From condensed version of Macaulay's theorem, we will have that cardinality of H minus 1 fold subset of A is larger than binomial coefficient of X minus 1, H minus 1. This we can say because all the prerequisite already satisfied in the theorem. Okay. Now, since we know that binomial coefficient of xh can be written as this form, simple calculation, so we can write this as h by x into binomial coefficient of xh. Okay. Now, I'm raising the left hand as power h. So we will have that this is greater than equal to this, and now replacing the previous value here, we will have this quantity. Now keeping a binomial coefficient xh, one binomial coefficient xh aside and replacing the remaining by cardinality of h-fold sumset of A, we will have this inequality. Therefore, we have that cardinality of h minus one-fold sumset of A power h is greater than equal to theta power h into cardinality of h-fold sumset of A power h minus 1. And this will basically give us our required result. On the other hand, since x is greater than equal to h, we can say that this will happen. And that concludes us that theta power h is greater than equal to 1. In particular, theta is greater than equal to 1. Okay. Now we will have a next nice result, which says that we know that already theta xh is basically h by x into binomial coefficient of xh power 1 by h. Now, if it happens that there is a real number x greater than equal to h such that by cardinality of h-fold sumset of A is equal to binomial coefficient of xh, then replacing this value here, we can say that theta can be written as h by x into cardinality of h-fold sumset of A power 1 by h. Therefore, from the previous theorem, we can conclude that if h greater than equal to 2 be an integer, and if n be a non-empty finite subset of an abelian group, then cardinality of h minus one-fold sumset of A is greater than equal to h by x into cardinality of h-fold sumset of A, where the real number x is greater than equal to h, and the cardinality of h-fold sumset of A is equal to binomial coefficient of xh. Now we have observed that we have this function theta. Now we will see that this theta has very nice property. So we would like to talk about this theta. Well, as I told that if theta is taking the value 1, this condensed version of Macaulay's theorem will give us the Plunakis result. But it says that if theta is taking the value more than 1, the result gives us a much stronger result. Okay, the theorem gives us a much stronger result. So here we observe that if x just crosses h, then theta will cross the value 1. So we will have much stronger value. And in particular, by elementary manipulation, using this thing, we can say that theta value will be strictly less than e. So theta will be always lying in between 1 and e. We also can be proved that if we fix the value h, then the mapping x goes to theta xh is basically an increasing function, strictly increasing function. Okay. Now this theta has some nice property as well. It's like it has some asymptotic behavior. For large values of x, this theta is asymptotically same as this function. And as extending to infinity, it is basically equal to this. Now, the proof of this can be done by using the following approximation formulas, these two approximation formulas. Okay. Now, if I draw the graph of theta for, let's say I'm fixing my value x to be equal to 1000, then its curve will be something like this. Now here, you can observe that if my h is something that half of this x, so let it be 500 around, then with the then values of theta will be something near to this 2. So in particular, if I consider for the high values of x as well, larger values of x, if I consider the h coordinate to be half of x, then we will find out that with the high probability, its value will be lying in the range of this 2. In particular, we are having that limit extending to infinity, theta x by 2 will be equal to 2. And also we have this thing. We further show that limit extending to infinity, theta x root x is equal to e. Well, now we are almost coming to the end. Let's talk about the future plan regarding this problem. First of all, at the very beginning, I have talked about the upper bound, which is this. We believe that it is an asymptotically optimal. And also we believe that for this upper bound will achieve for the equality, will achieve for large enough values of h. Also, the second problem I would like to take is that this upper bound is the best possible. Now, in which sense I am telling it to be the best possible? Suppose given any sequence of positive integers, if it happens that d0 equal to 1, and let's say di plus 1 is greater than equal to 1 and less than equal to di power bracket I, then there exists a finite subset A of a commutative semigroup G such that dH is equal to cardinality of HA. Okay, here there is one minor point one has to be, okay, it has to be a major point as well. So a major point one has to be pointed out that I'm not talking about a group here. I am saying that A is a finite subset of a semigroup. I believe that this part one can solve by using this by the sufficient part of the Macaulay's theorem. Well, this is the main part which I wanted to talk about my research. And here are a few references. So this first references give us the condensed version of Macaulay's theorem. This is our paper which is submitted already, and today I have talked about this paper only. The third paper, this is in 1927, it has been published, and we have taken the Macaulay's theorem from here. This is the most famous book, the Nathanson. So all the knowledge we have from this book. So Plunak's theory, this is we are having from this Nathanson book and this paper. So, and the graph theoretic estimate was there in this Nathanson book already. And this is a famous Tau and U book, which is useful for all purpose. Well, here I am concluding my talk. Thank you very much for your attention.
Okay. Any questions or comment, anything? Or if not, then I request all of you to just unmute yourself and thanks our speaker by just clapping. Thank you, Eshita, for giving such a nice talk. And for next talk of this series, we will meet again on next Wednesday, the same time, and our speaker will be Arvind Kumar from IIT Delhi. So,
thank you very much for giving me the opportunity to present my talk here, and it's a nice platform. Yeah, thanks a lot.
So yeah, I think we are ending this meeting for today. Okay, thank you all of you.
Thank you.